want to take a sort of a break from differentiation and do integration now. Less an intro to integration. When would we use integration? What is integration? Etc. So we're only going to be worried about polynomials for now. We will do trig functions and log functions and exponential functions a bit later on. But this is the IB formula, and this is the NCEA formula. So you'll see that the formulae are pretty much identical for integration. That's integration there, and that's integration there. The terminology is a bit different. The IB uses this integration symbol. Yeah, you can kind of use it, but these are equivalent statements. So what it says is that if we have a function and we integrate it, we do this to it, we do that to it. It's, if you have a look, these are the same formulae. So what is integration? Well, let's say we have a graph. So we've got a graph here, and I want to know the gradient when x equals 2. So there's x equals 2 there. So I want to know how steep that tangent there is. What am I going to do? Well, I've got f of x. I'm going to differentiate it, and you should be pretty good at it now. So 2 times 3 is 6, x, and we lose 1, minus 2 times 4, which is minus 8, x, and then we lose 1, and then the 3 disappears. Just take a note of that 3 disappearing there, because it's going to come back later on. What we would do then, if we want to find the slope when x equals 2, it's going to be 6 times 2 squared minus 8 times 2. So what's that? So 2 squared is 4. That's going to be 24 minus 16. So that's going to be 8. So in other words, for every 1 that it goes across, it's going to go up 8. Okay, so far so good. What though if we wanted to know the area under this curve? Well, then we would do integration. So integration kind of undoes differentiation. It's often called anti-differentiation. What does it mean? Well, it means the area there. But what is the area? Well, it's the collected amount of something. So if we have, and I can never remember which one is which, this is Hillary or Jupiter, I can never remember. I think it's Tenzing actually. The gradient would tell us how steep the slope is. We would integrate to find out how much mountain is underneath Tenzing there. So this is Tenzing or Hillary, 1953 when they first climbed Mount Everest. So this is the top of Mount Everest. So apart from people in airplanes, this guy is the highest. That's as high as you can go in the world while still having your feet in the feet on the ground, put it that way. Okay, so let's have a look to see what the mechanics of that actually are. And I'm going to change color from that pretty obnoxious red there to blue. So if we have the differential function and we want to integrate it, so say the differential function is, let's say ax to the power of n. If we wanted to differentiate it, what would we do? If we had ax n and we want to differentiate it, the a would stay there, the n would be multiplied by that, and then we would lose 1. We're going to do exactly the opposite when we anti-differentiate, as you might expect. So when we integrate that, the a is going to stay there, the x is going to stay there, and now instead of losing an n, we're going to add an n. And instead of multiplying by n, we divide by n plus 1. And if you have a look at the formula there, that's exactly what we've done. So this is the power rule for integration. My advice is to tattoo that onto the inside of your eyelids so you'll never forget it. And it's going to do 90% of the heavy lifting for integration, at least for polynomials anyway. Okay, let's look at another example of when we would use integration. This is a sort of an example. Let's say that you go to the bank, and on day one, you open a bank account and you put $1 into the account. And then on day 2, you put $2 into the account. Okay, with the amount that you put in, let's say the number of days, let's let the day number be X. So the amount that you put into the deposit is going to be equal to the number of the day. So on day 10, you put in $10. On day 12, you put $12 and so forth. What would be your balance after 2 days? Well, it's going to be pretty easy to find your balance. It's going to be 1 plus 2. So your balance after 2 days is going to be $3. So far, so good. What about though on day 12? Now what do we do? Well, we could have 1 plus 2 plus 3 up to plus 12, but it's going to get pretty monotonous pretty quickly. And that's when we would use integration. So we're going to apply the integration formula. So the amount that we deposit, which is how much the balance changes per day, is going to be X. So X is on day 1, we put in $1, day 2. So if X day, we put in X numbers of dollars. The balance is going to be, after we integrate it, how much mountain is underneath us at any one time. Well, if X is there, there's one X there and there's a 1 there. We don't show those obviously because it's pretty tedious to do that. The 1 is going to stay there. The X is going to stay there. This 1 in the indices is going to increase by 1, and we're going to divide by that number that we raised it by. And this is going to give us the balance at any time for X. Remember, X is the number of days. So therefore, on day 12, the balance on day 12 is going to be 12 squared divided by 2, which is 144, divided by 2, which is what, $72. This might be a strange example, but there's a lot of things in life that do, and in nature, that really do follow that pattern. So every day it grows by a little bit more than before. That's when we would use integration. All right, so what's the deal with the plus c? When we integrate, if we have f dash of x and we integrate that, we have to put a plus c. What does that mean? Why do we have to do that? And there was a bit of a hint before when we dealt with constants. Let's take this function here. This is the blue one here. So when we differentiate that, so f of x is 2x cubed minus 4x. When we differentiated that, if we differentiated it, it would be 6x squared minus 4. Okay. If we take this one here and we differentiate it, So this is the blue one here. If f of x is 2x cubed minus 4x plus 3, that's a bit of a wonky 3, f dash of x is going to be 6x squared minus 4. Look, that's exactly the same. But notice that this graph here and this graph here, obviously not the same graph. They're completely different graphs. They have the same shape, but they're kind of stacked one on top of each other. In fact, if we differentiate this one as well, we're going to get the same answer if we differentiate it. So adding that C kind of takes that into account. It sort of says when we differentiated it, when we differentiate a constant, if there's a plus C at the end of something that we need to differentiate, that constant disappears. So then when we come to integrate back, we have to sort of say, well, when we integrate it backwards, we may have lost some information that may have been there before we differentiated it. And for that reason, we have to have the plus C. It is always there because it's there. When we differentiate it, it disappears. So therefore, when we integrate it, it has to reappear. It's really, really important to know what that plus C is. And if most of the time, it's what's called the initial condition. So it would be something at time equals 0 if we're looking at time. Okay, so that's why we have the plus C at the end.